This is my geometry course. Today we're going to learn applications of triangle congruence and more triangle theorems, specifically the Isosceles Triangle Theorem and its converse and the Equilateral Triangle Theorem and its converse. And we're also going to learn the Hypotenuse-Leg Theorem, which is another triangle congruence theorem. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. We'll start with applications of triangle congruence. In a previous class, we stated the definition of polygon congruence. If you put that definition in if-then form, it says if corresponding parts of polygons are congruent, then the polygons are congruent. So that's the definition of congruent polygons. And again, that's in if-then form. But I don't know if I mentioned this, I forget if I mentioned this, but the converse of a definition is always true. Remember, when you just give some random statement, the converse is not necessarily true. Sometimes the converse is incorrect. But when it comes to a definition, when you're just, and remember, a definition is just something that you decide is true. You just say this is true by definition. It's just true because we make it true. The converse of a definition is always true. So that's an important thing to remember. So again, if we have this, the definition of congruent polygons, if we state that in if-then form, we can then reverse it and say if polygons are congruent, if we've shown that polygons are congruent, then that proves that corresponding parts are congruent. So that's just the converse of a definition. Now, if we apply this to triangles in particular, then we say corresponding parts of congruent triangles are congruent. So what this means is if we've shown that triangles are congruent, we've already shown that the triangles are congruent, we've proved that the triangles are congruent, then we can say corresponding parts of congruent triangles are congruent. And we have a special abbreviation for that, CPCTC. Now you're probably wondering, who cares? Why do we have to come up with that abbreviation? Well, we're going to use this so commonly in geometry class that we don't want to have to write this entire sentence out. So that's why we come up with that abbreviation CPCTC over here. It just makes it so we don't have to write that sentence out. So if you didn't understand all that, I know that is kind of complicated, but that's okay. When we do practice problems, you're going to see exactly what we're talking about. But before we go on, go ahead and take a screenshot of those highlighted sentences there, because you might want to look back at that. So we're going to do some proofs to demonstrate how CPCTC works. It says write two column proofs to show that the statements below are true. Now remember, I told you that proofs are a huge part of geometry class, and you're probably starting to realize why that is. We just keep doing more and more proofs. So let's get started with our first problem. If angle B is congruent to angle E, and angle A is congruent to angle D, and side AB is congruent to side DE, then side BC is congruent to side EF. Now I know that seems kind of complicated, but just look at the picture. It makes it really simple. So we have two angles that are congruent in both triangles, and we have a side that's congruent in both triangles. But we want to use this information that we have here, the congruency, to show that side BC, sorry about that, we want to show that side BC is congruent to side EF. All right? So what we're going to do is first we're going to show that the two triangles are congruent, and then we're going to say, okay, if the two triangles are congruent, that proves that corresponding parts must be congruent. So BC is congruent to EF. And the justification for that will be CPCTC. Corresponding parts of congruent triangles are congruent. So the good news about this class, or the first half of this class today, is that what we're going to be doing is exactly the same thing that we did in previous classes. We're just going to have one more step. So let's start with the given information. Angle B is congruent to angle E, and angle A is congruent to angle D. that's given. And we also know that AB is congruent to DE. That's given. And so that information proves that the two triangles are congruent. ABC is congruent to triangle DEF. And we know that by ASA, angle side angle. We learned that in a previous class. So now that we've shown that the two triangles are congruent, we know that those two triangles are congruent. We can say that side BC is congruent, and this is the whole point, is to show that by side BC is congruent to side EF. And we know that because of corresponding parts of congruent triangles are congruent. Now again, the most important thing to understand is that you only use this after you have proven that the triangles are congruent. So we prove that the triangles are congruent, and then we could use CPCTC. Don't use CPCTC before you prove that the triangles are congruent. So CPCTC, it's like stating a definition. One thing that you could say is it's just the definition of congruent triangles, but that's not really enough. You want to explain a little bit more, so you have to explain the converse of the definition of congruent triangles, and that is, if triangles are congruent, then corresponding parts are congruent. But we don't want to have to write all that out, so we just write CPCTC. All right, let's get on with the next problem. We're going to do one more of these before you try one on your own. So let's go ahead and just write the given information. All right, we have all the given information written down. So now we can see, obviously, that the triangles are congruent. Let's see here, that would be DEF, just want to make sure we get the right order. And that's SSS, the SSS triangle postulate. And if you don't know what this is, that means you haven't done the homework from the last class, so make sure you do that. So now we know the triangles are congruent by the SSS postulate, and now we can say that angle B is congruent to angle E by CPCTC. So again, we're just doing the exact same thing that we did in previous classes. The only difference is we have one more step. If we know the triangles are congruent, then we know corresponding parts are congruent. And if corresponding parts are congruent, that means that this part here, B, must be congruent to E. Angle B must be congruent to angle B. Angle B must be congruent to angle E. All right, so now, as you can see, it's pretty easy. We just have that one extra step there. So now I want you to try number 3, and when you come back, we'll do it together. All right, we're back. I'm going to state the given information. So that's all given. So with that information alone, we know that triangle ABC is congruent to triangle DEF. And we know that by the SAS postulate. You should have all those postulates memorized by now. If you don't, you can go back to the previous class and look at a screenshot of all those postulates. And if you don't remember the postulates, I'll put a screenshot of all the postulates and theorems we've learned so far. And hopefully I'll do that on the first problem. I'll go back in the editing and do that on the first problem. So now we know that those triangles are congruent by SAS. So because we know they're congruent, we know corresponding parts must be congruent. So that means side BC must be congruent to side EF because they're corresponding parts. And we can justify that by saying CPCTC. Corresponding parts of congruent triangles are congruent. So if you got those answers, good job. Whoops, forgot to put a segment line there. All right, so on to the next problem. Try number 4, and when you come back, we'll do it together. All right, we're back. Angle C is congruent to angle F, and angle A is congruent to angle D, and side BC is congruent to side EF. That's given information. And let's see here. And by the way, you can make one step for each one of these statements, or you can put them all in one statement. It's probably kind of a bit much to put them all in the same line, but I'm just doing that to save space. So now, with that information alone, we can prove the triangle ABC is congruent to triangle DEF. And we know that by the AAS theorem. That's actually a theorem. That's the only one of those triangle congruence statements that was a theorem. So now that we've proven that the triangles are congruent, we know that corresponding parts must be congruent. And that is by CPCTC. Corresponding parts of congruent triangles are congruent. So if you got those answers, good job. All right, now we're going to go on to some problems that are a little bit more challenging, but because of the last class, this really shouldn't be difficult for you. It's just basic stuff that you've seen 100 times. All right, we're going to do the first couple proofs together. So let's start with the given information, as usual. Remember, in proofs, you don't always start with the given information, but 90% of the time you do. Let's see here. I'm just going to do separate lines for each statement there. AB is congruent to CB. That is given. We've got our given information, and notice that these two sides are up against each other and lined up perfectly there. So we can that side is the same in both triangles, and we can show that by saying BD is congruent to itself. That is the reflexive property of congruence. And now we can use the side angle side congruence postulate for triangles. So triangle ABD is congruent to triangle CBD. And now that we know that they're congruent, we can say that angle A is congruent to angle C because corresponding parts of congruent triangles are congruent. So as you can see, it's not too bad. We're just doing one extra step. It's pretty much the same thing that we did in previous classes. Let's try another one of these together. As usual, we'll write down the given information. So that's given. We also know that BC bisects angle ABD, and that's given. Now remember, bisect means that it cuts this angle in half. So if it cuts that angle in half, that means that this angle is congruent to this angle. So ABC, angle ABC, must be congruent to angle DBC. And again, if you look at the definition of bisectors, sometimes you use measure, sometimes you use just the angle itself. But that's okay. You don't have to worry about that stuff, really. You can just go straight to the congruent statement. So that is the definition of angle bisector. We also know that side BC is congruent to itself. That is the reflexive property of congruence. So now, just to review what we have here, we were given the information that this side is congruent to this side. We were given the information that, well, obviously this side is congruent in both triangles, and we have this angle is congruent to this angle. So that is, as you can see, it's side angle side. So we're going to use the SAS postulate to show that the two triangles are congruent. So we'll write SAS and triangle ABC. I always try to use ABC, so if you want to work along with me, then always try to use ABC if you can, instead of BAC or CAB or so on and so forth. The triangle ABC is congruent to triangle DBC by the SAS postulate. And now that we know that the triangles are congruent, we can say that angle ACB is congruent to, or excuse me, angle ACB is congruent to angle DCB because of CPCTC. So let's do one more of these problems together before you try one on your own. Again, we'll start out with the given information. That's given. Now, some people might say, well, I don't want to do this stuff anymore. I've already done this in the previous class. I don't need to do any more of these. Well, yes, you do, because you're simultaneously learning CPCTC and you're reviewing how to do these proofs. The proofs are going to get more difficult, so you need to be really solid when it comes to these basic proofs. So I don't want to hear students saying, well, I'm just going to skip forward or I'm not going to do this. No, you are going to do this. Because if you don't do it, you're not going to have enough practice to get to the harder stuff. We also know that B is the midpoint of AE. That's given. And we're trying to show that B is the midpoint of CD. So this problem is a little bit more difficult. So first let's go to the definition of the midpoint. So if B is the midpoint of AE, then that means that AB must be congruent to BE. And that's just the definition of midpoint. Again, if B is the midpoint of AE, then obviously AB must be congruent to BE. And we also know by the vertical angles theorem that angle ABC is congruent to angle EBD. So we know that this angle must be congruent to this angle by the vertical angles theorem. So now we've got an angle here, an angle here, an angle here, an angle here, and this side and this side. So what that means is that we can use the AAS congruence postulate. So we can say that the triangles are congruent. Triangle ABC is congruent to triangle EBD by the AAS. Actually, that's the AAS theorem. I think I called it a postulate. I meant a theorem. So now we know that the two triangles are congruent. So if we know the two triangles are congruent, we know that corresponding parts must be congruent. So we now know that side DB is congruent to side BC. Now, why do we care about that? Corresponding parts of congruent triangles are congruent. But why do we care about that? Well, if DB is congruent to BC, then that proves that B is the midpoint of DC, because that's just the definition of the midpoint. So B is the midpoint of DC. And that's the definition of midpoint. And maybe I should write that as CD. It doesn't really matter, I guess, but I'm just going to write it as CD because we have CD up here. All right, so that was a little more challenging. Now we're going to go on to a problem for you to do. So on to number 8. So now it's time for you to try one of these problems. Go ahead and attempt number 8, and when you come back, we'll do it together. All right, we're back. We'll start out with the given information. We also know that BD is congruent to itself because that side is connected and they're lined up properly. Reflexive property of congruence. So now you can see that we can use the SSS postulate. Triangle ABD is congruent to triangle CDB. Make sure you get the proper order there. Now, you may have written a slightly different order as long as the corresponding parts are lined up. Again, there's 6 different ways to do this. So please understand that. So we know that that's true by the SSS postulate. And now that we know that's true, we can easily say that angle A is congruent to angle C by CPCTC. So if you got that right, good job. All right, on to number 9. Go ahead and attempt number 9 on your own, and when you come back, we'll do it together. All right, we're back. B is the midpoint of AE and DC. That's a given. And if that's true, that means that AB must be congruent to BE, and DB must be congruent to BC. Now, do you see why that's true? That's the definition of midpoint. If B is the midpoint of this segment and this segment, then that means by definition, this segment here must be congruent to this segment here, and this segment must be congruent to this segment, because again, that's just the definition of midpoint. It means that it cuts the segments in half. We can also say that angle ABC is congruent to angle EBD by the vertical angles theorem. So this angle must be congruent to this angle by the vertical angles theorem. So we have side angle side and side angle side. So we can use the SAS postulate to say that triangle ABC is congruent to triangle EBD. And now that we know that the triangles are congruent, we can say that side AC is congruent to side ED by CPCTC. So if you got that one right, good job. All right, why don't you try number 10? Number 10 is going to be more challenging. You're going to have to use one of the transversal postulates, so I'm going to put those up on the screen. So go ahead and try number 10, and when you come back, we'll do it together. All right, we're back. AB is parallel to ED. And that's given information. So what that means is that angle ABC must be congruent to angle EDC. And that is the alternate interior angles theorem. And you can abbreviate that if you want. You can write AI AT if you want. But I'm just going to write it out because I want you to know exactly what it is. So now I want you to be aware there's actually two ways you can do this. You can use the alternate interior angles theorem again. So we show that these angles are congruent by the alternate interior angles theorem. But you can also show that these angles are congruent. And then you can use AAS. That's one way to do it. Another way to do it is just to use the vertical angles theorem, and then you would use the ASA postulate. So that's what I'm going to do. So I'm going to say angle ACB is congruent to angle ECD by the vertical angles theorem. And now we can use ASA. Actually, no, we can't. I haven't said that we need to say BC is congruent to DC. That's given information. So now we can use ASA to say that triangle ABC is congruent to triangle EDC by the ASA postulate. And we're trying to show that C is the midpoint of AE. In order to show that C is the midpoint of AE, we have to show that AC is congruent to CE. But we know that those are congruent because those are corresponding parts of congruent triangles. We've already shown that the triangles are congruent. So now we can just say that side AC is congruent to side CE by CPCTC. Corresponding parts of congruent triangles are congruent. And now we can say that C is the midpoint of AE, and that is just the definition of midpoint. So that was a slightly more challenging problem, but if you got those answers, good job. All right, so that was CPCTC. You have to show that two triangles are congruent, and then you can say the corresponding parts of congruent triangles are congruent. Now we're going to go on to some additional triangle theorems. So this is the Isosceles Triangle Theorem. Now in a previous class we talked about what isosceles triangles are. Isosceles triangles are triangles where two sides are congruent. And it turns out actually three sides can be congruent in some cases, but you can just think of it as two sides are congruent. So what the Isosceles Triangle Theorem tells us is that if you have a triangle where two sides are congruent, the opposite angles must be congruent also. Now, what does opposite angle mean? Well, let's say that you're talking about this side over here. If you're talking about that side, the angle opposite that side is this angle. So it's just the angle that's across from that side. That's the easiest way to think of it. This angle is not across because this side is actually a part of that angle. And same thing over here. This side is actually a part of this angle over in the bottom right. But for this angle, this side is not a part of it at all. So that's why it's called the opposite angle. It's the angle across from it. So again, if you have two sides, this angle is opposite this side, and this angle is opposite this side. So again, if you have two sides that are congruent in a triangle, the angle's opposite. This angle is opposite this side, and this angle is opposite this side. Those angles must be congruent. All right, so let's do some practice problems just so you can, and first, go ahead and take a screenshot of that theorem. Now, we're not going to prove that theorem just because it's going to be boring to you. We could prove it. You have to use something called an auxiliary line. We could prove it, but most students are just going to get bored if we try to prove that. So we'll maybe prove that towards the end of the course. But for now, we just need to figure out what it is. So we're going to do some practice problems. In the following problems, we don't have to do formal proofs because, again, if we do formal proofs for every single problem we do, it's going to get tedious. So in these problems, we don't have to do formal proofs. Now, we have a triangle that is isosceles because two sides are congruent. We have this side is congruent to this side. So because those two sides are congruent, because it's an isosceles triangle, that means that angles opposite those sides must be congruent. So what that means is that if this top angle is 80 degrees, then the bottom angle must be 80 degrees also. So that's what we're trying to find. It says find the measure of angle B. So we can say the measure of angle B is 80 degrees. So that was really easy. This part of the class is going to be actually pretty easy for the most part. Let's try some more of these before you try one on your own. So for number 12, you can see that this is an isosceles triangle because two of the sides are the same length. We have 43 meters. And in my course so far, I haven't really put units for some of these sides, but I just want you to be aware that sometimes you will see units. So that's 43 meters and 43 meters. So it's an isosceles triangle. So that means the side opposite this angle, if it's 75 degrees, or the side opposite, the angle opposite this side, if that's 75 degrees, then the other angle over here that's opposite 43 must be 75 also. Now just be aware that we don't know what this angle is unless we use the triangle sum theorem. So don't confuse those angles. We're looking for the measure of angle D. So the measure of angle D is 75 degrees. So again, these problems are very easy. All right, number 13, we're looking for x. Now, we know this is isosceles because two of the sides are 100. That means by the isosceles triangle theorem, these two angles, they must be congruent. So 5x must be equal to 25 degrees. So 5x must be equal to 25 degrees. And using that equation, we can find x. Divide both sides by 5, and we get x is equal to 5. For number 14, this is an isosceles triangle because this side is congruent to this side. We know that by those red tick marks. But if those sides are congruent, that means the angles opposite those sides must be congruent also. So that means that 4x plus 5 must be equal to 6x minus 15. And we're going to use that to find x. So we're going to subtract 4x from both sides, and we get 2x minus 15 is equal to 5. Add 15 to both sides, and we get 20 is equal to 2x. Divide both sides by 2, and we get x is equal to 10. Now, this is kind of a trick problem because we're not looking for x. In this problem, we're looking for the measure of angle C. Now, we're going to use x equals 10 to find the measure of angle C. We're looking for this angle. We need to know what this angle is here. So this problem is a little bit more complicated. So we can plug in 10 for x and use the triangle sum theorem to find that angle. So 10 times 6 is 60. 60 minus 15 is 45. So I know that angle is 45, and I'm going to take the triangle out here and write 45. And if I plug in 10 here, 10 times 4 is 40, and then 40 plus 5 is 45. So I know this angle must be 45. Now I can find this angle by using the triangle sum theorem. I know that all those angles must add up to 180 degrees. So we'll just call this angle, we'll just call it C. That's what it is. So 45 plus 45 plus measure of angle C, that must be equal to 180 degrees. So if that's equal to 180 degrees, we can just solve that equation. And it's pretty simple stuff. We can see that measure of angle C is equal to 90 degrees. So some of these problems get a little harder because sometimes you're asked to find this angle, and sometimes you're asked to find this angle, which requires the triangle sum theorem. So just be aware of that. Don't get tricked. You got to find the measure of the angle that they're looking for. All right, so now it's time for you to try. We're going to start off with some easy ones here. So again, use your Isosceles Triangle Theorem. If two sides of a triangle are congruent, that means the sides are the angles opposite those sides are congruent. So try number 15, and when you come back, we'll do it together. All right, we're back. The measure of angle C must be 77 degrees. So if you got 77 degrees, good job. And again, these are the angles that are opposite those congruent sides. We know the sides are congruent because they're both 30 centimeters. So angle C is 77 degrees. Try number 16, and when you come back, we'll do it together. All right, we're back. We know that these two sides are congruent, so it's an isosceles triangle, so we can use the Isosceles Triangle Theorem. And if we know that this angle is 50 degrees, if we know that E is 50 degrees, that means that F must be 50 degrees also. So we can say the measure of angle F is 50 degrees. So if you got that problem right, good job. All right, so let's try some problems that are a little bit harder. Try number 17, and when you come back, we'll do it together. All right, we're back. So we can see that this is isosceles because 3.5 feet is that's the length of two sides, so it's an isosceles triangle. So that means that angle 7x must be equal to angle 5x plus 12. Subtract 5x from both sides, and we get 2x is equal to 12. Divide both sides by 2, and we get x is equal to 6. So if you got 6 for x, good job. Now for 17, don't get fooled. We're looking for the measure of angle E. Okay, you have to find y first, but then you have to use that to find the measure of angle E. So try number 18, and when you come back, we'll do it together. All right, we're back. So it's an isosceles, so we know that 8y minus 2 must be equal to negative 2y plus 88. Then we can add 2y to both sides. Then we can add 2 to both sides. Divide both sides by 10, and we get y is equal to 9. Now we can go up here. Again, you're going to run out of room a lot when you're taking various courses and doing various tests. That's normal to run out of room. It happens all the time. So just use an arrow. And we want to find the measure of angle E. So we're going to plug in 9 here, and we get 72 minus 2 is 70. So that means the other angle must be 70 also. So we have a triangle where we have 70 degrees and we have 70 degrees. So we just have to use the triangle sum theorem to find the measure of angle E. So 70 degrees plus 70 degrees plus measure of angle E is equal to 180 degrees. And doing the math on that, we can see measure of angle E must be 40 degrees. So we got 40 degrees, good job. If you didn't get 40 degrees, that's okay. Just go back and figure out what you did wrong. So now we're going to go to the Isosceles Triangle Converse Theorem. This is just the converse of the theorem that we just used. If two angles in a triangle are congruent, then the sides opposite of those angles must be congruent also. So that's very simple. If you have an isosceles triangle, that means, well, it doesn't have to be defined as isosceles, but if these two angles are congruent, that proves by this theorem that these two sides are congruent. So we're just going backwards. So let's try number 19 together. Now we have two congruent angles. So that means the sides opposite those angles must be congruent, but we know this side is 16. So that means that this side must be 16 also. So the length of BC is 16 meters. So pretty easy stuff. Now this next triangle, number 20, we have two angles that are congruent, so that means the sides opposite must be congruent. So if CB is 10, that means AB must be 10 also. So again, sometimes you have units, sometimes you have something like meters, sometimes you have no units. If there's no units, don't write units. If there is units, write units. All right, on to number 21. So again, we're just doing things backwards. So now we have two angles that are congruent, so that means the sides opposite must be congruent. So 4 must be equal to negative 3x plus 10. Subtract 10 from both sides, and we get negative 6 is equal to negative 3x. Divide both sides by negative 3, and we get x is equal to 2. So we found x. So now, problem that's a little more challenging. Again, we have two angles that are congruent, so that means that the opposite sides of those angles must be congruent. And again, you can't make the mistake of saying that this side is congruent to something, because we don't know that. We just know the sides opposite the angles are congruent. So subtract 4y from both sides. Subtract 2 from both sides. Divide both sides by 2, and we get y is equal to 3. And I guess that's all we were looking for in that problem. Y is equal to 3. If we were looking for this angle, then, well, actually, we really couldn't find that angle. All right. So now it's time for you to try some problems. Again, we're using the Isosceles Triangle Converse Theorem. If you didn't get a screenshot of that, go ahead and get a screenshot. And try number 23. And when you come back, we'll do it together. All right, we're back. Two angles are the same, so that means that the opposite sides of those angles must be the same. So BC must be 15. So no units for that one. If you got that one, good job. All right, try number 24. When you come back, we'll do it together. All right, we're back. We've got two congruent angles, so the sides opposite must be congruent. So if you got 3 4/5 millimeters, good job. That's what mm means. It means millimeters. All right, on to a little more challenging problem. So try 25, and when you come back, we'll do it together. All right, we're back. 2x plus 2 must be equal to 5x minus 7. Subtract 2x from both sides. And add 7 to both sides. Divide both sides by 3. I'm going to put an arrow up here, and we get x is equal to 3. So if you got that answer, good job. Try number 26, and when you come back, we'll do it together. All right, we're back. We have two angles that are congruent, so the sides opposite those angles must be congruent. Divide both sides by 10, and we get y is equal to 4. So if you got 4, good job. All right, so we learned the Isosceles Triangle Theorem and the Isosceles Triangle Converse Theorem. So now we're going to do some proofs. So we'll do this first one together. If measure of angle A is 68 degrees, so let's go ahead and write that. Measure of angle A is 68 degrees. That's a given. This is going to be an isosceles triangle proof. And we know that side AC is congruent to side BC. That's a given. Now we know that angle A must be congruent to angle B. Now how do we know that? Well, that's the Isosceles Triangle Theorem. If two sides of a triangle are congruent, then the sides opposite must be congruent also. Or excuse me, the angles opposite those sides must be congruent also. So angle A is congruent to angle B. So now we can say that the measure of angle A is equal to the measure of angle B, and that's just the definition of congruent angles. And we know that the measure of angle A is 68 degrees, and we know the measure of angle A is also equal to the measure of angle B. So we have two things that are both equal to the same thing. So if 68 is A and B is also A, then that means that the measure of angle B must be 68 degrees. And that is the transitive property of equality. So that was just one example of a proof that would actually use the Isosceles Triangle Theorem. So why don't you try one of those proofs? But you're going to use the Isosceles Triangle Converse Theorem. So go ahead and try number 28, and when you come back, we'll do it together. All right, we're back. AB is 211. And that's given. And we know that angle A is congruent to angle C. That's given. So if angle A is congruent to angle C, we know that side AB must be congruent to side BC by the Isosceles Triangle Converse Theorem. So by definition, we know that AB must be equal to BC. That's just the definition of congruent segments. And we know that AB is 211, but AB is also BC. So we have two things that are both equal to AB, so that means that BC must be equal to 211. And that is the transitive property of equality. So if you got those answers, good job. All right, now we're going to go on to the Equilateral Triangle Theorem. If a triangle is equilateral, then it is equiangular. So go ahead and get screenshots of those theorems. And while you're at it, go ahead and get a screenshot of this theorem too. These are the last three theorems we're going to use today. So if you have a triangle that is equilateral, and remember, equilateral means that all the sides are congruent. So you can see here that all the sides are congruent. If you have a triangle that is equilateral, that proves that it's equiangular. Okay? Now we have another theorem that says if a triangle is equiangular, then the measure of every interior angle must be 60 degrees. And you can prove that very easily. I'm not going to bore you with the proof, but I think we've actually done that proof in a previous, I think you were given it in a homework problem. If you know that a triangle is equiangular, meaning all the angles are equal, then you can easily use the triangle sum theorem to show that each angle must be 60 degrees. Because if you have angle A plus angle A plus angle A, you know all angles are equal and you know they add up to 180, then you can show with very simple algebra that A must be 60 degrees. So because we know that this is a equilateral triangle, we know that it's equiangular, and because it's equiangular, we know that the measure of angle E must be equal to 60 degrees. So that's very easy. These are going to be problems that are even easier than the previous ones that we did. Again, if you didn't get a screenshot of those three theorems. All right, so number 30, we have an equilateral triangle because all the sides are congruent, which means we know that all the angles must be 60 degrees. So that means that 4x must be equal to 60, and we can easily find x, which is 15. Again, these problems are very easy. Now we're looking for the measure of angle D. We can see that this is an equilateral triangle. Why don't you go ahead and try number 31. We can see it's an equilateral triangle, so you can easily find the measure of angle D. When you come back, we'll do it together. All right, we're back. Measure of angle D is equal to 60 degrees. Because it's equilateral, it must be equiangular, and because it's equiangular, it must be all the angles must be 60 degrees. Try number 32, and when you come back, we'll do it together. All right, we're back. Because the triangle is equilateral, using those two theorems again, we know that the angle must be equal to 60 degrees. So we'll just set that equal to 60, subtract 20 from both sides, and you get 8x is equal to 40. Divide both sides by 8, and we get x is equal to 5. So if you got 5, good job. If you didn't get 5, that's okay. Just go back and figure out what you did wrong. All right, so now we go to the equilateral triangle converse theorem. So if a triangle is equiangular, if we know the angles are the same, then we know it's equilateral, meaning all the sides must be congruent. So we have all the sides congruent here. So that we have all the angles are congruent, so that proves that all the sides must be congruent. So obviously HI must be 5 inches. For number 34, we have, it's a little bit harder, we have two angles are 60. Now, if we know that those two angles are 60, because we have to show that it's equiangular, but we don't know all the angles. But if we know that these two sides are, if we know that these two angles are 60, we can use the triangle sum theorem to find that this angle is also 60. Now, I don't think I have to use the triangle sum theorem. You can just do the arithmetic in your head. Again, we have to have 60 plus what equals 180. We know that all the angles must add up to 180, so obviously angle C is 60 degrees. Hopefully you see that. Okay, I could show the math, but I don't really think it's necessary. So angle C must be 60 degrees, but if angle C is 60 degrees, that means this triangle is equiangular. But according to this theorem up here, if the triangle is equiangular, that proves that it's equilateral, meaning all the sides are congruent. But if all the sides are congruent, that means that we can say that this side, 2x minus 4, must be equal to negative x plus 11. So all we have to do is just solve that equation, add x to both sides, and add 4 to both sides, and we get 3x is equal to 15, divide both sides by 3, and we get x is equal to 5. So again, these problems are fairly simple. So now it's time for you to try a problem. Try number 35, and again, if you didn't get a screenshot of that theorem, and you can look at these example problems also if you need to. All right, let's try one more together before you try one on your own. This is an equiangular triangle, because I see those green arcs. So by the equilateral triangle converse theorem, you can see up there, we know that the sides must be congruent. So 2x minus 10 must be equal to x minus 4. Subtract x from both sides. And add 10 to both sides. And we get x is equal to 6. But don't stop there. Don't get fooled. A lot of students would stop there. We're not looking for x. We're looking for JL. So now we have to actually find the length of all the sides. Now we know that the triangle is equilateral. We know all the sides must be the same length. So what we can do is we can plug in 6 to one of these expressions and find the length of JK, for example. And once we find the length of JK, we know that JL has to be the same length. So if you plug it in, I guess I can just show it. JL is equal to JK, and JK is equal to 2 times 6 minus 10, which is 2. So the answer is 2. All right, so now it's time for you to try a problem. We're starting off with an easy one here. So do number 36, and when you come back, we'll do it together. All right, we're back. We know that this triangle is equiangular. Because it's equiangular, it must be equilateral, meaning all the sides must be congruent. So side ED must be equal to 62, and side DF must also be equal to 62. So in that problem, we were looking for two quantities there. So remember, you got to read those directions carefully. All right, so on to number 37. We're almost done today. You're doing good. Try number 37, and when you come back, we'll do it together. All right, we're back. This is an equiangular triangle, which means that all the sides must be congruent. So that means that 3x must be equal to 18. Divide both sides by 3, and x must be equal to 6. So if you got 6, good job. All right, so we know that two angles are 60 degrees, but that means by the triangle sum theorem, if you just do the basic math, B must be 60 degrees also. So try number 38, and when you come back, we'll do it together. All right, we're back. So we know that this must be an equiangular triangle because all the angles must be 60 degrees, just using the triangle sum theorem. So that proves that it's equilateral, meaning all sides are congruent. So the lengths must be equal. Subtract x from both sides. Add 1 to both sides. And we know that x is equal to 4, but we're not looking for x. We're looking for BC. So now we know that BC is equal to x plus 3. And we know x is 4. So we can just plug in 4 there. 4 plus 3 is equal to 7. So BC is equal to 7. If you got 7, good job. It's very common for students to accidentally stop once they get to this point. But we're not looking for x. You got to read the directions carefully. We're looking for BC. So if you got that one right, good job. Now we're going to do some proofs. We'll do the first proof together. If triangle GHI below is an equiangular triangle and HI is 12 millimeters, then GI is 12 millimeters. So triangle GHI is equiangular. That's given information. Now, if triangle GHI is equiangular, then that proves that triangle GHI is equilateral. So how do we know that? Well, we know that by the Equilateral Triangle Converse Theorem. If a triangle is equiangular, then it must be equilateral. So GHI is equilateral. So that is the Equilateral Triangle Converse Theorem. And if GHI is equilateral, that means that HI must be equal to GI. That is the definition of equilateral triangles. Now we're also given the information that HI, we're told that HI is equal to 12 millimeters. So we need one more step here. GI and 12 are both equal to HI. So that means that GI must be equal to 12 millimeters. And that's what we're trying to prove. Actually, I forgot to write given. That's given information. And then the last part was the transitive property of equality. All right. So now I want you to try one of those types of problems. In this problem, you're going to use the Equilateral Triangle Theorem. So go ahead and try number 40, and when you come back, we'll do it together. All right, we're back. We know that AB is equal to AC, which is also equal to BC. So that's just a quick way of writing the equality of those three values that is given. Now, if we know that all those sides are equal, then by definition they're all congruent. I guess we can say that. Sometimes you might skip this step, but I guess we should just write that. That is the definition of congruent segments. So we know that all the sides are congruent now. So if all the sides are congruent, that means that the triangle is equilateral. So triangle ABC is equilateral. And that's just the definition of an equilateral triangle. Now we have that theorem that says if a triangle is equilateral, then it must be equiangular. So triangle ABC is equiangular, and that is the Equilateral Triangle Theorem. If ABC is equilateral, then it must be equiangular. So now we can say, because it's equiangular, we can use this theorem here. If we know it's equiangular, then all angles must be 60 degrees. And that is called the Equiangular Triangle Theorem. So I'm going to go ahead and write that. Because of the Equiangular Triangle Theorem, we know that all the angles must be 60 degrees. The measures of all the angles must be 60 degrees. So that was the answer for number 40. If you got that answer, good job. Now we're going to go on to the Hypotenuse-Leg Congruence Theorem. Now we learned the SSS postulate, the SAS postulate, the ASA postulate, and the AAS theorem in a previous class. Those are theorems that show that triangles are congruent with that given information. We're now going to present a fifth statement called the Hypotenuse-Leg Congruence Theorem. Now it's very important to understand that this theorem only applies to right triangles. You can't use it on any other type of triangle, only right triangles. Now before we talk about this theorem in detail, let's review our our terminology for right triangles. In a previous class, we learned that the side opposite the right angle, so here's the right angle, the side opposite that right angle, meaning across from the right angle, is called the hypotenuse. It's given a special name. And that's only for right triangles. That weird word hypotenuse is only used for the side opposite the right angle in right triangles. The word's not used for any other triangles. And the other sides of a right triangle are called legs. So these are called legs. Now the Hypotenuse-Leg Congruence Theorem says that if you have two right triangles, for example, you have two right triangles here. We know they're right because we see the green right angle there. If you have two right triangles and you know that the hypotenuses are congruent, and there's also one leg that's congruent in each triangle, we have a leg here, that information alone proves that these two triangles are congruent. Now, let me explain why this is significant. Now, notice we have side angle. In previous classes, we learned that there is no such thing as an SSA postulate or theorem. The SSA idea or statement does not work. But here we have SSA, and it does work. The reason that it works is, again, this is a special case where you have right triangles. And if you want to prove that it works, you use the Pythagorean theorem. We learned the Pythagorean theorem in a previous class. If you know that the hypotenuse in each triangle, the hypotenuses are congruent, and you know there's a leg in each triangle that's congruent, then by using the Pythagorean theorem, you can show that the third sides must be congruent also. And then you can easily prove that the triangles are congruent. So again, that's why this hypotenuse-leg theorem works for right triangles. It works in this special case. But again, it's very important to understand that this theorem only works for right triangles. So let's do the first problem here. It says, determine if the triangles below are congruent. If so, state the postulate or theorem used. So again, we have two right triangles, and the hypotenuses are congruent, and one leg in each triangle is congruent to the other leg. And so because these are both right triangles, we can use that hypotenuse-leg congruence theorem and say that these two triangles are congruent by HL. We'll just abbreviate it HL. So we abbreviated the other statements as SSS, SAS, ASA, and AAS, and so the hypotenuse-leg congruence theorem is abbreviated HL. So go ahead and get a screenshot of that theorem, and we'll go on to the next problem. But again, the most important thing is to understand you can only use the hypotenuse-leg theorem when you're dealing with right triangles. So are we dealing with right triangles in this next problem? Yes, we are, because we see the right angle there. And we have a hypotenuse. The hypotenuse is opposite the right angle, so the hypotenuses are congruent. They're both 10. And we also have a leg that's congruent in both triangles. They're both 8. So we can use the hypotenuse-leg congruence theorem. We can say that these triangles are congruent by HL. Let's do another problem. 43. We have right triangles, so we might be able to use the hypotenuse-leg congruence theorem. But notice that we don't have a hypotenuse. The side opposite the 90-degree angle, we don't have that side. We actually have the legs. The legs are congruent. We have 5 on both triangles for legs, and we have 4 for the other legs. So we can't use the HL congruence theorem But we can say that the triangles are congruent by SAS, side angle side. So we can say that they're congruent. We just can't use the hypotenuse-leg theorem because we don't have the hypotenuses. All right, let's try two more of these problems. So the first thing we need to ask is, do we have right triangles? And the answer is no, we do not. Well, technically we don't really know for sure, but we just know that we don't have enough information. This might be a right angle, but we just don't know. Because again, it's not a box. Remember, you have to have a box. That shows that it's a right angle. This green arc here is not a box. So we can't use the HL theorem. So can we use any other theorems or postulates? Well, we have side, angle. So is there an SSA postulate or theorem? And the answer is no. Remember, we learned that. There is no SSA postulate or theorem, so we can say not enough information. We don't know for sure that they're not congruent, but we just know that we can't prove that they're congruent. There's not enough information. All right, let's try one more of these together before we try some on your own. So first question, are these right triangles? Yes, they are, because we want to know if we can use the HL theorem. That's what we're practicing here. So they are right triangles, so we might be able to use the HL theorem. We have the hypotenuses. Remember, the hypotenuses are opposite the right angle. So they're both 50.6, so they're congruent. And we have a leg in both triangles that's congruent. So we can use the HL theorem. So we can say, yes, they're congruent by HL. All right, it's time for you to try some problems. Try number 46, and when you come back, we'll do it together. All right, we're back. The hypotenuses are both 17. Well, first of all, these are right triangles. That's the first thing we need to establish. And the hypotenuses are both 17, and we have a leg that's 8 in both triangles. So yes, we can say that they're congruent by HL. So if you got that answer, good job. All right, try number 47, and when you come back, we'll do it together. All right, we're back. So first thing we need to figure out is, are these right triangles? And yes, they are. And can we use the hypotenuse-leg congruence theorem? Well, we need the hypotenuses to be congruent, and we see that they are. They're both 7. But we also need a leg, and we don't have a leg. So we cannot use the hypotenuse-leg congruence theorem. But can we still prove that the triangles are congruent? And the answer is yes, we can, because we have angle, side. There is an AAS theorem that tells us that triangles are congruent. So we have two right angles and two arcs that are the same, and the hypotenuses. So we can say that these triangles are congruent by AAS. So if you got that answer, good job. We could not use the HL theorem, but we can use the AAS theorem. So again, if you got that answer, good job. Try number 48, and when you come back, we'll do it together. All right, we're back. We have two right triangles, and the hypotenuses are congruent. And we have a leg in each triangle that's congruent. So we can use the HL theorem to say that these two triangles are congruent. So if you got that answer, good job. All right, try number 49, and when you come back, we'll do it together. All right, we're back. So the first question we need to ask is, do we have right triangles? And the answer is, we don't really know. If this angle had a little box, then we would know for sure that we're dealing with right triangles, but it doesn't have a box. So that means that there's not enough information. So we can't use the HL theorem, and we only have two sides in each triangle that we know are congruent, so that's not enough information. So we say not enough information. So if you got that answer, good job. All right, so now we're going to go on to some proofs. It says use the HL theorem in two-column proofs to show that the following statements are true. So we're going to use the HL theorem in these proofs. If triangle ABC and triangle DEF are right triangles, so we know they're right triangles, and AB is congruent to DE, and AC is congruent to DF, then angle F is congruent to angle C. Now we're going to have to use the CPCTC concept, or the converse of that definition. So let's start out with the given information. Triangle ABC and triangle DEF are right triangles. And that's given. And AB is congruent to DE. And AC is congruent to DF. That's also given information. So AB and DE are legs, and AC and DF are hypotenuses. So it looks like we can use the HL theorem to show that these two triangles are congruent. We can't use SSA because that's not a postulate, but if you have right triangles, you can use HL. So we can say that triangle ABC is congruent to triangle DEF by the HL theorem. So now that we know that the triangles are congruent, we can say that corresponding parts are congruent. So we now know that angle F is congruent to angle C by CPCTC, because those are corresponding parts. Those are corresponding angles. So that was just one example of how you would use HL in a proof. Now let's do one more of these together before you try some proofs on your own. If AC is perpendicular to BD and AD is congruent to DC, then blah, blah, blah. Let's start with the given information. So AC is perpendicular. Remember that that's a special symbol for perpendicular. So they're perpendicular, and that is given. Now, if they're perpendicular, then remember, by definition, that means angle ABD and also angle CBD are right angles. So this angle here and this angle, they're right angles because, again, AC is perpendicular to BD. So again, the definition of perpendicular means that they form 90-degree angles. So that's the definition of perpendicular. Now we also know that side AD is congruent to side DC, and that's given. And we also know that side BD is congruent to itself. That's how we show that BD is common. It's a common side to both triangles. And that's the reflexive property of congruence. So with all that information, we can see that these are right triangles for one thing, because these are right angles. So we're dealing with two right triangles. This triangle and this triangle, they're both right triangles. And we know that the hypotenuses are congruent because we were told that AD is congruent to DC. And we also know that there's one leg that's congruent because this side is common to both triangles, and that would be a leg of those two right triangles. So we have enough information to use the HL congruence theorem. So we can say that triangle ABD is congruent to triangle CBD by HL. So now that we know that these two triangles are congruent, we can say that angle ADB is congruent to angle CDB. And that's what we're trying to prove, because corresponding parts of congruent triangles are congruent. So again, once we show that the triangles are congruent, we can use CPCTC to show that any other corresponding part of the two triangles, parts of the two triangles are congruent. All right, so that proof was a little more difficult than the previous proof. So now I want you to try some proofs. Try number 52. And when you come back, we'll do it together. All right, we're back. We know that angle B and angle D are right angles. And we know that BC is congruent to DC. That's all given information. And as in the previous problem, we know that AC is congruent to itself. That's how we show that AC is common to both triangles, and that's the reflexive property of congruence. So AC, if you didn't notice, AC is the hypotenuse for both triangles. So we know that the hypotenuses of the two triangles are congruent. And we also know that BC and DC are congruent, so that's a leg in each triangle. And of course, because angle B and angle D are right angles, we know that triangle ABC and triangle ADC are right triangles, so we can use the HL congruence theorem. So at this point, we know that triangle ABC, is congruent to triangle ADC by the HL theorem. That's all we had to prove, is that the triangles are congruent. If you got those answers, good job. So it looks like we're going to try one more problem. Go ahead and attempt number 53. Looks like you're going to have to use CPCTC as well as the HL congruence theorem. So try 53, and when you come back, we'll do it together. All right, we're back. AB is perpendicular to BC, and DC is perpendicular to BC. What that information tells us is that angle ABC and angle BCD, you can call it BCD or DCB, or you can call this angle ABC or CBA, it doesn't really matter. Those two angles are right angles, and that is just the definition of perpendicular. So again, AB is perpendicular to BC, which means the angle formed by those two segments is 90 degrees, or they're right angles. And DC is perpendicular to BC, so the angle formed here is a right angle. We also know that side AC is congruent to side DB. We were given that information. And we know by the reflexive property of congruence, BC is congruent to BC. Well, actually, we just know that because we can see it in the picture, but we justify it with the reflexive property of congruence. That's just tradition. So we know that these are right triangles, ABC and also DCB are right triangles because these are right angles. And we also know that there's one leg in both triangles, that's congruent because it's common to both triangles. And we know that the hypotenuses that are opposite the 90-degree angles, those are congruent because we're given that information. AC is congruent to DB. So given all that information, we can use the HL congruence theorem to say that triangle ABC is congruent to triangle DCB by the HL theorem. And now that we know those triangles are congruent, we can say that corresponding parts are congruent, so angle A must be congruent to angle D by CPCTC. That's just the converse of the definition of congruent polygons. Congruent parts of congruent triangles are congruent. So if you got those answers, good job. So that was the geometry class today. And let's get screenshots of all the work that we did. You can use these screenshots to help you with your homework or to study for tests. Now don't go before you get your homework. Get screenshots of these homework pages. There's page 1 and page 2. Or screenshot rather. Screenshot 3. Screenshot 4. And screenshot 5. But don't go until you get the answers to the proofs. Here's the answers to the proofs. Remember, you got to check your answers. If you don't check your answers, then you're wasting your time. It's not enough just to attempt the homework, you have to do it correctly and completely and neatly. And more important than anything else, you have to know where your homework is. If you do the homework and then lose it and you don't put it in your binder in the right chronological order, then this entire course is a complete waste of time. So again, remember, if you don't do your homework, it's a 100% guarantee you're going to learn nothing in this entire course. So get that homework done, and I'll look forward to seeing you in the next class.